Columbia University. Oh, maybe I should say this again. Okay, it's like welcome everyone. It's a great pleasure to have Mehtaab Sawhney today from Columbia University. Mehtaab Sawhney is a Cray Research Fellow and the author of many amazing breakthroughs in additive combinatorics and related areas. Today, he's here to tell us about one such exciting development. Mehtaab, thank you for agreeing to give this talk. Floor is yours, or screen is yours.
Great, and thanks for the invitation. So today I'll be discussing quasi-polynomial bounds for the corners theorem, and everything I'm discussing is based on joint work with four wonderful co-authors, Michael Jabber, who's a graduate student at UT Austin, Yang Liu, who's at CMU, Shachar, who's at UCSD, and Anthony Ostuni, who's a grad student at UCSD. So maybe the starting point of everything I'm discussing is a well-known theorem of Roth from 53. So let A be a subset of bracket n, and by bracket n I mean the first n positive integers, 1 through n, having no three-term arithmetic progression. And AP here will always be shorthand for arithmetic progression. Then the size of A is bounded by the size of n by n divided by log n. And okay, so a 3AP, just for clarity, is x plus y, x plus 2y. And okay, we want it to be a non-trivial thing, so y is not equal to 0. And just another bit of notation, this means hiding an absolute constant. I'll be a little bit sloppy throughout with asymptotic notation, so if at any point somebody gets confused, please do just feel free to ask a question. So bounds on what's called Roth's theorem have been a topic of intensive study. So after a series of improvements, by a rather distinguished group of researchers. So first Heath Brown, then Semiretti, independently, Semiretti, then Bourgain, then Sanders, then Blum-Sisask, and I'm omitting a few names. These are maybe the most important. There was a really remarkable result now 2 years ago by Xander Kelly and Raghu Meka, so 23. So let A be 1 through n with no three-term arithmetic progression. So the same setup as before, but they obtained the remarkably stronger quantitative bound. They obtained that A is bounded by n times e to the minus log n to some power. Let's say, I'm not going to write a power. They get 1/12, I believe. And that constant 1/12 has then been refined by Bloom and Sisask. But they sort of show that versus the trivial bound of n, you can save a quasi-polynomial amount. And the reason this is remarkable is that there's a theorem due to Berend, which says that there exists A with no three-term arithmetic progression such that A is bounded below by e to the minus c square root log n. So you can't hope to save a power of n, but you can hope to save this quasi-polynomial amount. And what this work of Kelly and Mecca did, sort of before their work, everybody was saving some power of the logarithm versus the trivial bound. And here they're saving a quasi-polynomial amount, which is roughly close to the truth by this Berend example. So I mean, there is still some gap. We don't know that the exponent's a half, but okay, we're sort of within striking distance of the truth. So Roth's theorem has been generalized in many ways. And okay, so the one that we'll concern ourselves with is a theorem of Einstein-Semiretti, which goes under the name Corner's theorem. So this was proven in 74. So we have now, instead of taking a subset of the integers, we have A, which is a subset of the grid. With the size of A, let's say we know it's a positive fraction, so it's bigger than delta n squared. So if n is greater than some function n of delta, there exists d greater than 0 such that xy, x plus dy, x, y plus d are all in A. So what does this look like? This is 3 points which form an axis-aligned right triangle, and we're saying that they're all in A. So this is saying that so if you look at a set with positive density, then it always contains this configuration. If you take the contrapositive, if you have a set which avoids such a configuration, then it has to have density little o of n squared. So the original proof of Einstein-Semiretti used Semiretti's theorem, so in an incredibly beautiful but rather elaborate way. So they essentially gave no quantitative bounds. It can be thought of as almost a purely qualitative statement. And this sort of falls in the line of getting quantitative bounds for the multidimensional Semiretti theorem. So, so getting bounds for the multidimensional Semiretti theorem is a key open research direction. So what I'm saying is, so okay, we can restrict ourselves to 2D. You can fix any, so here I fixed 3 points which form our axis-aligned right triangle, and I'm guaranteed that there's some, up to translation and dilation, there exists a copy of that inside my set. What Furstenberg and Katznelson proved using ergodic methods is that if I fix any constellation of points, then such a theorem is true. But because they used ergodic theory, they got no quantitative bounds. And we have quantitative bounds in 2 cases. So case 1 is the Corner's theorem. So looks like this. So then it was shown by Shkredov that instead of just this qualitative thing, we have that A is at most of size. Suppose you have a set A avoiding such a configuration, then it has size at most n squared divided by log n to the power omega 1. And so this is by Shkredov. So first he saved a triple log and then he improved it. So in 05 he saved a triple log, and then in 06 he improved it to save a double log. And we literally have exactly one further pattern. This is, so it's 3 points in the line and then 1, so this kind of L shape. And here we have a bound of the size of A divided by n squared divided by some number of logs depending on the current state of the literature. But this was done in really quite a difficult paper of Saropoulos. And for instance, you could ask for axis-aligned squares, and this is a complete mystery. There is real. I think this is a problem that many people have thought about, and it's sort of an extremely difficult problem. So really, the goal of the talk will not be to make progress on this direction, but sort of we're going to try to improve one. So the main result, as mentioned before, so this joint work with Gerbert, Jean Glue, Shachar Lovett, Anthony Ostuni. And so this was from earlier this year. So let A be a subset of n by n with the size of A being bigger than n squared times e to the minus log n. Okay, sorry, the way I'm stating it. Okay, I'm hiding, suppose it's bigger by some large absolute constant times 1 over 600. Then A contains xy, x plus dy, x, y plus d with d greater than 0. Okay. So in particular, we're improving Shkredov's bound, which saved a power of a double logarithm to a quasi-polynomial. And there's a slight adaptation of the construction of Barron gives a similar lower bound. So up to this 1 over 600 not being a half, this is the sharp bound. Okay. So the primary goal for the talk is to explain why Shkredov first loses these two logarithms, and then maybe explain the key technical ingredient to win back one of them. So as with many of these problems, it's so I phrased everything in terms of the interval 1 through n. It's often much simpler to instead look at what's called the finite field model case. And for much of our work, it's sort of very convenient to do this. So I have A, which is a subset of f2 to the n cross f2 to the n with the size of A being alpha times n 4 to the n. So this set A has density alpha. The indicator function of A, xy, this is 1 if xy is an A and 0 otherwise. So this is just the indicator function. And for many computations, we don't want to operate with A, but instead with the balanced indicator function of A. So you take the indicator of A and subtract off alpha, which is the mean. Okay, so what is the assumption that, let's look at the assumption that we have no corners analytically. So that corresponds to the indicator function of A, xy, indicator function of A, x plus z times y, indicator function of A, x, y plus z. This is at most alpha cubed over 2. So actually, it's very close to 0. If A has no corners, then the only contribution to this expectation is when z equals 0. But let's be generous. Say we don't if A was a random set, this would have size alpha cubed. We're saying, okay, suppose we're 1/2 what the random amount is. Okay, so let's make a couple of easy transformations. So there's one convenient change of variables. First, we set z equal to x plus y plus z. So just change z to be that. And I'm hiding one small step, but it's very easy to sort of get to the assumption that the indicator function of A, xy, indicator function, fa of xy, indicator function y plus z, y. So this is why I want to operate over f2 to the n, because if I substitute z equals x plus y plus z, you get 2z plus y plus z, but 2z vanishes because we're in characteristic 2. So this is just for the convenience of not needing negative signs. And you do the same thing here, you get the following assumption. So the lower bound becomes an upper bound. So we get that this is at least alpha cubed over 2. Okay. So this is, I'm taking the average over x, y, and z. So first let me pull out the expectation. So let's first apply the triangle inequality. I pull out expectation of y and z. I'm left with an expectation over x on the inside. I get fa of xy, indicator function of a, x plus z. This is bigger than alpha cubed over 2. So this is just the triangle inequality. Okay. I then do Cauchy-Schwarz. So I get to square the inside. So if I square the inside, I get the expectation over x, fa, xy, indicator function of a, x plus z, all squared. This is going to be bigger than alpha to the sixth over 4. And because it's a square, I can expand it out. And since everything's real valued, I don't need to put complex conjugates. Okay, so now I'm just going to pull out the average over z on the outside, z x1, x2 on the outside, and I'll just be left with the average over y on the inside of fa of x1y, fa of x2y. So this is, I'm just applying the triangle inequality again. I get it's bigger than alpha to the sixth over 4. So this is just, so I've expanded out the square and then applied triangle inequality. And finally, I can apply Cauchy-Schwarz again. And what I get is that, so I square and then expand it out. And if you get it out, what you get is the average over x1, x2, y1, y2, fa, x1, y1, fa, x1, y2, fa, x2, y1, fa, x2, y2. This is bigger than alpha to the 12 over 16. It really doesn't matter what this is. This is just alpha to some power. Okay. So if you haven't followed exactly what I've done, that doesn't matter. The point is I've done some number of Cauchy-Schwarzes and I got to this analytical conclusion. The key point will now be what can we derive from this analytical conclusion and sort of what does our loss become. So what does this mean? So this is sort of counting 4 cycles in some weighted graph. So okay, maybe let's phrase it slightly different. Let me phrase it in terms of a graph nicely. So I have my vertex set. One side is f2 to the n, the other side is f2 to the n. And the weight I give to an edge xy is the indicator that it's in the set minus alpha. So this is some weighted graph. And this quantity I'm looking at is the 4 cycle count in this bipartite graph. And I'm getting that the weighted 4 cycle count is large. So there's what's called the theory of quasi-random graphs, which lets you derive a conclusion from this. What the theory of quasi-random graphs, so okay, you can either call this quasi-random graphs, or, I mean, if you're less familiar with this, you can just sort of observe that this is like some weighted adjacency matrix, and I'm taking the 4th power of it, and I'm saying the trace of the 4th power is large. If the trace of the 4th power is large, it has a large eigenvalue, a large singular value, and you can derive the same conclusion I'm about to write. So what happens is that there exists h1 and h2, which are one-bounded functions such that the expectation of h1 of x, h2 of y, fa of xy, or this is bigger than alpha to the O1. So there, I mean, you can also sort of, by writing this out, there exists sets x, which is a subset of f2 to the n, and y, which is a subset of f2 to the n, and say that the expectation of the indicator function of x, this is bigger than some power in alpha. The expectation of the indicator function of y is bigger than some power of alpha. And we have that the expectation of the indicator function of x, the indicator function of a, x, y, indicator function of y, this is bigger than alpha plus alpha to some power times the expectation of the indicator function of x, the indicator function of y, of x, y of y. Okay, maybe less formally, what I'm saying here is I can find two very large vertex subsets where my set has increased density on this rectangle. So because my graph was not quasi-random, I can do this. So, okay, so this suggests to use what's called the density increment strategy. So we now pass from f2 to the n cross f2 to the n to x times y with density increasing from alpha to alpha plus alpha to the O1. So that's the first thing. But I mean, that's quite problematic because currently x and y are completely arbitrary sets. We have no control on them. They could be arbitrary subsets of f2 to the n. And this argument, we were assuming we're in f2 to the n times f2 to the n and not in some arbitrary product set. So the second step, so this is step one. Step two, and this is maybe the main innovation of Shkredov's work. So what you can do is Shkredov splits x and y into Fourier pseudo-random pieces of codimension alpha to the minus O1. Okay, so very roughly what you can do is you can split your set X into a bunch of pieces such that so each piece then doesn't have a large Fourier coefficient with respect to the subspace it lies in. And then you can sort of split into these subspaces and then pick where your set is large on one of the product sets. And because your host sets X and Y are Fourier pseudo-random, it turns out you can run this proof. I don't want to get into that. It's a technical matter, but sort of once you have X and Y being Fourier pseudo-random, you can think this is in some sense they look like the entire set, and that's enough to run the argument. The issue is, so why Shkredov loses is that, so why does he lose two logs? So first, going from alpha to alpha plus alpha to the O1, this costs you one logarithm. And so this is step one. And step two, this pseudo-randomization this costs one extra logarithm. So you have these logarithms, they change, so this costs you the two logarithms in the final bound. And the goal is to sort of avoid both of these losses when going through the proof. Okay, so very roughly what we do, so R1 star is, okay, we replace we do the obvious thing, we get a multiplicative density increment for the first step. And then for our second step, we have pseudo-randomization. Which costs sort of instead of costing codimension, which is polynomial in the density, we have pseudo-randomization, which only costs logarithmically in the codimension. It turns out if you just work through the recursion, this gives the quasi-polynomial bounds I claimed. Okay. So at this point, you can sort of this is sort of the strategy, and the heart is actually getting this to work. There are sort of lots of technical details. So this broad outline is maybe the idea, but you sort of need to implement each step. Okay, so what I want to zoom in on is sort of maybe the one general purpose tool which comes up in sort of handling one, which is it's a little bit difficult to explain where it comes from, but I'll sort of explain where it shows up in our setting, and then explain what you need to do to solve it. So, okay.
Mehtaab one.
So it turns out that if you want to do the Cauchy-Schwarz thing in a way which works out so that you can get something like 1 star, you'll have that your set xy, it doesn't live in just a product set x times y, but instead lives in some more complicated host set. So it lives in x cross x, y of y, and d of x plus y. So what I'm saying here is that, and okay, the expectation of x equals delta x, and so on. So what I'm saying here is that I have a subset of f2 to the n cross f2 to the n, where I'm fixing the first coordinate to be inside capital X, the second coordinate to be inside capital Y, and the sum of the two coordinates to be inside some third set D. Why you need this
One
falls
quick
out of the
question.
Cauchy-Schwarz.
Can I ask one quick question before you go on more about 1 star? I wanted to ask something quick about 2 star. Does your 2 star step also improve the Sarah's results? Like, do you remove some logs from there with the pseudo-randomization step?
Not easily, because our pseudo-randomization is really with respect. So yeah, so this argument of 2 uses some kind of L2 strategy. This L2 strategy you can use sort of in higher order cases. What we use for 2 star is density with respect to Bohr sets. And this sort of more physical space description really only works in the context of Bohr sets right now. Maybe if you had correct inverse theorems, you could do it, but that's not so clear either.
Got it. Thank you. Sorry.
Yeah. Okay. So okay, let's maybe set this up. So okay, so we want this host to look nice. So you should think of as A inside this host set, this host set, and we're going to assume that X, Y, and D are sort of nice in all the senses. I don't want to be so precise about it. It turns out to complicate matters. It's useful not to sort of think about that first. But one thing you have of the host set is that they sort of act like X, Y, and D were random. So the expectation of X of X, Y of Y, D of X plus Y is delta X, delta Y, delta D. And this would be true if X, Y, and D had no large Fourier coefficients. So then we need to say what it means for A to have density alpha. So that no longer means it has density alpha. What it means is it has density alpha with respect to its host. So is alpha relative density. Okay. So, okay. So using Holder's inequality in a very careful way, plus a technique called spectral positivity. So this is one of the key ideas in the work of Kelly and Mecca, but we really need a more recent variant due to Kelly, Lovett, Mecca. Sort of maybe the main thing is to realize that this is secretly an inequality about graphs and stuff. So what you can prove is that you take the expectation over x1, x2, and then y1 through yk. What you'll get is that the indicator of A, xi, yj, so I is in 2, j is in k. This is bigger than 1 plus omega 1 to the k, alpha to the 2k, delta x squared, delta y to the k, delta d to the 2k. Okay, so let's figure out why is this a reasonable thing to start with, and then B will sort of start to interpret it slowly. So the first thing is explaining these factors of delta. So observe that there are only 2 distinct values of x here. x1 and x2. So that's where you get the x squared from, delta x squared from. There are k distinct values of y, y1, y2, all the way to yk. So that's why there's a delta y to the k. And there's 2k different values for the sum, xi plus yk. And so that's where you get the delta d to the 2k. So that's sort of the random prediction. And then there are 2k copies of a. So this is where you get the alpha to the 2k. And what we're saying here is that we have like exponentially more, like 1.001 to the k more copies. So this is sort of, I'm saying I have like, I'm saying for each edge in this, so this is like counting copies in some complete, this is like counting some copies of some complete bipartite graph. So I have k vertices in y and 2 vertices in x. And for each edge, I'm sort of getting a constant amount of boost. So that's the assumption. So basically, this holdering is replacing a C4 by a slightly more complicated graph. But there's something quite strange about this graph. Okay, so it turns out for normalization reasons, I don't want to, let me sort of make this look a little bit prettier. So here in the above expression, I had x1 and x2 living inside f2 to the n. It turns out to be better to say x1 and x2 live inside x, and y1 through yk, this lives inside capital Y. So then I get something that looks a little bit prettier. I and 2, j and k. The indicator function of a of xi, yj, this is bigger than 1 plus omega 1 times alpha times delta d to the power 2k. So I just sort of folded in the vertex factors of x and y into the expectation. So if you look at this, where is this delta d factor coming in? This delta d factor is coming in where sort of, okay, originally I had x and y and f2 to the end, but now sort of imagine I've restricted the first vertex set to x and the second vertex set to y. There's sort of a graph gamma, which is above. This is just the indicator that x plus y is inside my set D. And that graph has density delta D. Okay, and my function, my set A is sort of an alpha fraction of that. So the real goal you want to be able to extract is the following. So what do we want to show? So what I want to show is that there exists h1 and h2 with the following property. So h1 of x. So h1 and h2 are non-negative one-bounded functions such that first I sort of get a multiplicative density increment. So it's the density instead of being alpha times delta d is is it's a constant factor bigger, and I have that the expectation of x these HIs, these sets, they're quite large. They're e to the minus k to the O1. So I lose something in the exponential on the size of the graph times log 1 over alpha to the O1. Okay. So here's the sort of key point about this entire statement. The key point here is this is log 1 over alpha and not log 1 over alpha delta d. So I'm able to see that my function has increased density on a very large rectangle. But the size of that rectangle does not depend on my true density. My true density is alpha times delta d. But instead only depends on my density relative to some container set. Okay, so in this kind of generality, I need some assumption on gamma. And we'll show this under the assumption that gamma is pseudorandom. So the rest of the talk will just be explaining the precise graph theoretic statement and how you prove it. Okay, for various reasons, we're going to sort of abstract out the problem. So I have a graph G, x, y, which is inside some pseudo-random graph gamma, x, y. So the graph gamma has density mu. This is what's delta D above. G has density alpha times mu. And what I'm going to assume is that the expectation, so instead of doing this more complicated bipartite graph, this is already interesting for C4. It's some constant fraction larger than alpha to the fourth, mu to the fourth. Okay, so keeping on writing this is going to get really, really cumbersome. So what I'm actually just going to do is I'm going to denote this by this. So this is a graph with 4 vertices. I'm taking the average. This is bigger than 1 plus omega 1, alpha to the fourth, mu to the fourth. Okay. So this is just a graphical representation of the inequality above. Okay. And what I'm going to assume is gamma is pseudorandom. We're not going to sort of say what this exactly means. We'll sort of see what falls out of the proof. And the proof will give you something very natural. Okay. So the first step is to apply Holder's inequality. So Holder's inequality. So what you can do is you can sort of take G and you take sort of K pages of a book. And sort of all the edges have G on them. And then you multiply it by G to the power K minus 1. So basically, if you write out Holders correctly, this tells you this is bigger than this graph to the power K. And so this is bigger than 1 plus omega 1 to the K, alpha to the 4K, mu to the 4K. So this is just Holder's inequality. Now recall that this is the density of an edge. So this is alpha times mu. So if you rearrange, this tells you G, this graph. And so every edge here has a G on it. This is bigger than 1 plus omega 1 to the K, alpha to the 3K plus 1, mu to the 3K plus 1. Okay. To this point, I've just done a single application of Holder's inequality and nothing else. Okay. So now I need to use somewhere that I have a pseudo-random major end. So what I'm going to do is I'm going to say, let's look at that G. I'm just going to erase it and replace it by a gamma. What I mean by this is I'm counting graphs where this particular edge I count with respect to the graph gamma and the remaining edges are all in G. Okay, I can do that because G is less than gamma and everything is a non-negative function here. Okay, but now I get to use something. I get to use that gamma is a pseudo-random graph. So if you write down pseudo-randomness in the correct way, what that means is that that's the same thing as instead of having gamma there, I could just replace it by the constant function mu. And if you rearrange that, what you get is you instead get this graph. So I've sort of deleted this one edge, and there's like K of these pages coming off. This is bigger than 1 plus omega 1 to the K, alpha to the 3K plus 1, mu to the 3K. So there are 3K edges, and it looks like this. And one final trick is, okay, if I take k, which is say log 1 over alpha, and I choose parameters carefully, I make it a large constant times 1 over alpha, there's sort of a difference of one factor of alpha here between this and this. I can sort of just sort of by changing the implicit constant instead make this 1 plus omega 1 to the power k, alpha to the 3k, mu to the 3k. Okay, so I've done a bunch of inequalities. And what have I done? I've gone from the C4 graph that looks simpler, and I got this more complicated graph. So it seems like I haven't done anything. In reality, this graph is much simpler. The reason is this graph is girth 6, and hence simpler for our purposes. Okay. So the point will be now to look at graphs of girth 6 and try to understand them and sort of try to prove this kind of statement we want. Now this is a kind of ugly looking graph of girth 6. There are simpler graphs in the world of girth 6. The simplest such graph is a cycle of length 6. So our assumption looks we're instead going to study the following slightly simpler problem. So alpha to the 6th, mu to the 6th. I'm not really hiding anything. I just don't want to draw a really complicated diagram. So the key fact about C6 that we're going to use is that it's girth 6. Okay. So again, instead of doing this, I can actually make my life even simpler, sort of by iteratively removing an edge. Instead of looking at this assumption, I can instead sort of ask that it's bigger than alpha times mu times the corresponding 5 cycle. Like so a 5 path. So I'm sort of removing one edge and I gained a factor of alpha times mu times some constant. And the reason you can do this is suppose this didn't happen, then you could go from the 5 path, remove an edge, and at one of these steps you have to have such a boost. So this is just I've done some kind of telescoping to get here. So this is sort of this is the central thing. And at this point, the proof from here uses a crucial idea. Uses an idea called densification of Conlon-Fox-Shao. And I mean, so they applied it. So the version we're using is the version for graphs. The version for hypergraphs is analogous, sort of, but it's incredibly important. It was used sort of by the authors to give a much simpler proof of the relative similarity theorem, which is essentially the main ingredient in the work of Green and Tao on their famous thing, the primes contain arbitrarily long arithmetic progressions. But sort of that idea, how the technique there is what we actually need. So, okay. So let me label this vertex at the top x1, label this vertex at the top y1, and okay. Okay, so I have this assumption. So this is my assumption. By sort of basically linearity, I can choose x and y, or let me call them x tilde and y tilde. What I mean by this, I'm actually just choosing like where these vertices land. So I get to fix them and I have this inequality. So there exists a choice x tilde and y tilde such that this inequality is true. Okay, because x tilde and y tilde are fixed, I can sort of just erase this edge down here. It doesn't really matter anymore. It's like some fixed absolute value, so I can sort of erase it downstairs. Okay, and I get some diagram like this. Okay. So now what I'm going to do is define the function g1 of x1. So what is this going to be? It's basically going to be this codegree count. So it's the expectation of g of x1 y, so I'm averaging over y, g of y x tilde. So this is just this like codegree count, basically. I can then define g2 of y1. This is the expectation over x of g of y1 x, g of x, y tilde. So this is this edge here. And let's look at what we've written. So I claim this inequality star. Star is literally, I mean, I'm just rewriting out the expression. It's g1 x1 times the g of x1 y1 g2 of y1. This is bigger than 1 plus omega 1 alpha mu expectation of g1 x1 g2 y1. I've literally just written out the expressions, the diagram in terms of equations. So this almost looks like what we want, but okay, what do we expect that we expect the expectation of gi of g of x1, we sort of expect, it's easy to guarantee that it's bounded by alpha to the O1 times mu squared. So that's problematic because I promised you that I want these functions gi, I want that their expectations don't depend on mu. There's some power of alpha. But let's look at this. I claim that g1, okay, so the key point here is the following. So g1 of x1, well, I'm going to claim that's a function which is bounded by mu squared. So by the pseudo-randomness property, it's bounded by gamma of x1 y, gamma of y x tilde. This is just by the fact that g is bounded by gamma. And so this is now some codegree count in a pseudo-random graph. And okay, this is not true literally always, but for our purposes, you can actually just basically assume that this is just literally bounded by mu squared always. And so then what you can do is you can just define g1 tilde as g1 over mu squared. So then you have that g1 tilde it's bounded by 1. So I'm not lying. I haven't sort of like scaled away the issue. And its expectation of, so I can do the same thing for g2, or sorry, divided by mu squared. So the expectation of gi, this is bigger than some power of alpha. So it's not, so trickle no longer depends on mu. And I have the desired inequality that g1 tilde of x, g2 tilde of y, g of xy, this is bigger than 1 plus omega 1 alpha times mu expectation of g1 tilde, g2 tilde. Okay, so maybe let me step back and say what are we actually doing here? This seems like I did some manipulations and somehow it worked. What's actually happening here at the heart of the matter is that normally when you have a graph inside some pseudo-random graph, that the pseudo-random graph is not it's not that nice. But once you take a codegree count or some larger like larger count, then it acts like a regular object. It sort of looks like a dense graph up to some scaling issues. And by exploiting that fact, we're able to create these dense sets. So maybe the motto is that co-degree counts in pseudo-random graphs are much, much nicer objects. And by interpreting the problem we want as sort of these functions, instead of them being choosing vertices, instead if you use co-degrees, it turns to work out in your favor. And that's sort of the key point that's happening. And okay, so this is roughly how we handle one. So maybe, okay, I promised that I would say, let me just say one sentence about what's happening with two. So the key things to observe is sort of what is the pseudo-randomness condition? So the only pseudo-randomness it turns out you need is that the expectation of h1 of x times, so we sort of only need an upper bound constraint. We need that this is essentially always bounded by 1 plus epsilon times mu times the expectation of h1 of x, h2 of y, where h1 and h2 are non-negative functions. So the reason I'm saying this is every time we invoked this pseudo-random major, all we did was we said we're going to replace g by gamma and then say that gamma looks like mu. But we only ever needed an upper bound sense. So this is the only pseudo-randomness we need. And recall in our case that gamma of xy, it turns out in the relevant application is d of x plus y. So what we need to do is we need to understand what happens if h1 of x, d of x plus y, h2 of y, this is bigger than 1 plus epsilon times mu times expectation of h1 of x, h2 of y. And the key point is the work of Kelly and Mecca provides a good inverse theorem for this. So essentially the technical heart of the work of Kelly and Mecca is they say, suppose this condition is violent, like this condition holds, then D has large density, in particular density 1 plus epsilon times mu on a subspace of small codimension. So that's sort of where it enters. So this allows you to do the second step pseudo-randomization efficiently. Now, okay, I'm hiding every technical detail about how you get all these things to interlace, but that's sort of maybe how you get started. I mean, these 2 points are really what gave us hope when we were working on the problem. Okay, and with that, that's actually all I plan to say, so thanks.
Yeah, let's thank Mehtaab for the really nice talk. Thank you, Mehtaab.